On the 7th of September, 1945, the cobblestones of a destroyed Berlin carried the weight of history in a way that no city had ever carried it before. 4 nations that had spent 6 years trying to kill each other's soldiers were parading their finest military hardware through the same streets, in the same formation, past the same reviewing stands. The occasion was the formal recognition that the killing had stopped. What each nation brought to that parade said something about who they believed themselves to be and what they believed the future would require. The British brought their Comets and their brand-new Centurions, sleek, capable machines that represented the best their engineering tradition had produced. The Americans rolled their Shermans and their Pershings through the broken city, demonstrating the industrial scale that had overwhelmed Germany's technical sophistication. The French contributed what they had, which was not much after 5 years of occupation and collaboration. And then the Soviet vehicles appeared. The Western military observers who watched the Soviet armor pass through Berlin that day were professional soldiers with years of experience evaluating military equipment. They had been briefed on what Soviet production had looked like from intelligence reports. They thought they knew what to expect. They were wrong. The heavy tank that led the Soviet heavy armor column was not the machine they had been anticipating. It was lower than Western heavy tanks. Its hull front had a geometry, a curved, sloped form that Western designers had not adopted, that made the frontal projection seem to absorb the available sight lines rather than presenting them with a flat surface to measure. The turret was a flattened hemisphere with angles of inclination that the observers, doing rapid mental geometry, recognized as dramatically more effective than the numbers describing the raw plate thickness would suggest.
The gun that protruded from that turret was large. Not large in the relative sense of any comparison to what Western armies were fielding, but large in the absolute sense. A weapon whose caliber would have been more appropriate on a naval destroyer than on a ground vehicle. The intelligence cables that went back to London that evening were not routine. Their contents described a vehicle that outclassed in every dimension of armor and armament anything that British ground forces could currently field. The best British tank at that moment, the Centurion, had frontal protection that the reported Soviet gun could defeat from distances well beyond the range at which the British gun could reliably threaten the Soviet armor. The older vehicles that still made up the majority of British tank strength were not even a meaningful comparison. British military planners who read those cables and did the subsequent analysis were left with a conclusion that was simple to state and deeply uncomfortable to absorb. If the Soviet Union chose to push west into Europe with the armor it had just demonstrated in Berlin, the British Army's tank forces could not stop it. Not with what existed. Not without something fundamentally different. The Defense Ministry discussions that followed asked a question that had a technically demanding and financially alarming answer. What would it take to guarantee penetration of Soviet heavy tank armor at operational combat ranges? The question was put to the engineers and ordnance specialists who spent their careers thinking about exactly this problem. And the answer they produced was the number that reoriented the entire program. 183 millimeters. That was the barrel bore diameter required, according to the analysis, to guarantee the penetration performance the specification demanded.
Not with an armor-piercing shot in the conventional sense. The ballistics of a projectile that large at the required velocity created engineering problems of their own. But using a specific type of warhead that the British had developed and were continuing to refine. One that defeated armor not by punching through it, but by detonating against its outer surface and exploiting the internal spalling that the explosion generated. The figure of 183 millimeters was not an aspiration or an approximation. It was the calculated minimum to meet the requirement with available technology. And it was a number that, when placed in context, forced everyone in the room to acknowledge that what they were proposing had never been done before. A gun of this bore diameter, mounted on a mobile vehicle,
was not an engineering extrapolation of existing practice. It was a different category of problem entirely. The largest guns on the largest warships of the Second World War had operated in this caliber range. Proposing to mount something comparable on a tracked vehicle that would fight alongside infantry on a European battlefield was the kind of idea that engineers with experience immediately recognized as either revolutionary or catastrophically misguided, with the specific category undetermined until someone actually tried. The specification was written and issued, and the engineers at the Royal Ordnance establishments who received it did what engineers do. They set about finding out whether it was possible. The gun that resulted from this work received a formal designation and entered the record books immediately, because there was nothing comparable to it in the entire history of self-propelled land warfare. The barrel alone was more than 7 meters long, longer than most urban vehicles, and weighed nearly 3 tons before the mounting hardware, the recoil mechanism, and the breech assembly were added. The complete weapon installation in its mount represented a structural and mechanical challenge that the engineers acknowledged openly. They were designing something for which there was no precedent, no established practice to draw on, and no prior art that could tell them where the failure modes would appear. The ammunition was its own engineering problem. The projectile weighed between 65 and 70 kilograms, depending on the specific variant, roughly the weight of an adult person, and it was a 2-piece round. The shell body went into the breech first. Then a separate brass cartridge case containing the propellant charge, itself weighing over 30 kilograms, had to be loaded behind it. The complete loaded round stood nearly 1.5 meters tall. The physics of handling this ammunition inside a vehicle by human beings working in the confined space that armored vehicles necessarily provided was analyzed, and the conclusion was the same from every direction. One person could not do it. 2 people working together might be able to do it, under ideal conditions, at a rate of approximately 2 rounds per minute, which was slow even by the standards of the heavy tank guns of the period. The choice of vehicle to carry this weapon required a decision about what trade-offs were acceptable, and 4 conceptual options were put forward. A full turret tank with complete armor protection was immediately recognized as impractical. The weight of providing meaningful armor protection for a vehicle carrying a gun this size would have produced a machine too heavy to move on most European roads and bridges. A fully armored casemate with restricted traverse was more feasible in weight terms, but created tactical limitations that the Army found unacceptable. A lightly armored rotating mount split the difference in a way that satisfied neither requirement fully, but was at least buildable. And a bare carrier with no armor at all, a pure gun platform that accepted complete vulnerability in exchange for maximum simplicity, was theoretically available as an option, but was dismissed almost immediately as incompatible with any realistic combat employment. The decision was to use a rotating mount with light armor protection on the chassis of the most capable medium tank currently in British service. The choice of chassis was partly pragmatic. The vehicle was available, its mechanical systems were understood, and the Army already had the logistical infrastructure to support it, and partly a matter of the intended program structure. The gun carrier was explicitly conceived as an interim development platform, a vehicle on which the engineering problems of operating a 183mm weapon could be identified and solved before the definitive mount was developed for a heavier chassis then under development. Nobody described the interim vehicle as a combat-ready weapon. It was, in the formal language of the program documents, a test bed. 2 prototypes were built to different configurations, reflecting 2 different approaches to the fundamental problems of operating the gun. The first was simpler in its crew arrangements and protection, stripping away everything that was not directly necessary to fire the weapon. The gun sat in an open mounting without any enclosure for the crew, who operated it in the open air, exposed to everything that the battlefield environment would produce. The logic was that an enclosed space adequate to contain both the gun mechanism and a working crew would impose weight penalties that the chassis could not support, and that the test phase was primarily concerned with the gun's behavior rather than with crew habitability. A revolving drum mechanism, intended to pre-position rounds for loading, was incorporated, operating on the principle of a very large version of a revolver's cylinder, rotating the next round into position for the loaders to complete the loading cycle. The second prototype enclosed its crew in a steel box, whose dimensions were constrained by the weight limit the chassis imposed. The armor on this enclosure was 14 millimeters, enough to stop small arms fire and shell fragments at range, but not enough to provide meaningful protection against anything that a combat environment would plausibly direct at the vehicle. The crews who later conducted trials in this prototype described the experience of being inside it during firing as resembling being inside a large bell, while someone struck it repeatedly with a sledgehammer. This description was not hyperbolic. Before the first prototype was taken out for firing trials, the engineers made a decision that spoke clearly to what they expected would happen when the gun discharged. A ground anchor, a heavy steel blade that could be lowered from the rear of the vehicle to bite into the earth before firing, was fitted to prevent the machine from moving rearward under the recoil impulse. The concept of anchoring a tank to the ground to prevent it from being shoved backward by its own gun was not something that appeared in any prior discussion of armored vehicle design. It was an improvised solution to a problem that had no precedent. The first firing trials produced results that justified both the precaution and the anxiety. When the gun fired, the 50-ton vehicle pitched, the nose rising by more than 20 centimeters, while the rear dropped by more than 10. The numbers recorded in the trial reports were precise and alarming. At a 3-degree elevation angle, the front of the vehicle moved nearly 30 centimeters upward and the rear nearly 20 centimeters downward in response to a single shot.
Without the ground anchor, the vehicle translated rearward by nearly 1/4 of a meter. With the anchor engaged, the displacement was reduced but not eliminated. The engineers who had designed the recoil management system watched these results and understood immediately that the problem was not going to be solved by refinement of the existing design. The forces involved were not marginally outside acceptable limits. They were categorically beyond what the chassis had been designed to handle. Every shot was a structural event as much as a ballistic one, and the cumulative effect of repeated structural events on components that had not been designed for them was predictable and not favorable. The lateral firing test confirmed what the initial results had implied. When the gun was traversed 90 degrees to the side and fired, the vehicle responded in ways that the report described in language that was carefully factual and deeply unsettling. The oscillations transmitted to the hull were severe in both amplitude and frequency. The vehicle moved sideways. Internal components that were not part of the firing mechanism, brackets, fittings, structural elements, experienced loads that had not been considered in their design. The vertical elevation mechanism failed. When the engineers examined why, they found that the shock wave from the lateral discharge had bent the internal components of the mechanism and sheared the fasteners that held them in place. The gun had broken the machine it was mounted on. The second prototype accumulated 133 firing rounds during its test program. Each of those rounds provided data. Much of that data confirmed and quantified what the initial tests had suggested: that the relationship between the gun and the vehicle was fundamentally problematic in ways that could not be resolved by local engineering fixes. The chassis was not strong enough for the weapon. The weapon was not manageable at the operational tempo that combat would require. The ammunition was not handleable by any realistic crew arrangement in any realistic time frame. There was one more problem that accumulated alongside the structural and handling issues, and it was a problem that no amount of engineering refinement could address. The accuracy of the gun at maximum range was affected by weather in ways that smaller caliber guns were not.
A 70-kilogram projectile in flight has significantly more frontal area relative to its mass than a smaller round, and wind acts on that frontal area throughout the entire flight time. At 2 kilometers in, anything more than a light breeze, the deviation from the intended point of impact was large enough to introduce genuine uncertainty about whether a specific vehicle would be hit by a round aimed at it. The gun could guarantee penetration of whatever it hit. It could not guarantee hitting what it was aimed at. The engineering program continued through the mid-1950s with the institutional momentum of programs that have absorbed significant investment and have not yet reached a formal decision point. But the external environment was changing in ways that made the program's eventual cancellation increasingly inevitable before that decision point arrived. The technology that made the 183mm gun concept obsolete did not emerge from any tank development program. It came from a completely different direction, from the work being done on guided missiles, on the application of control systems and rocket propulsion to weapons that could be steered to their targets rather than aimed at the position where the target currently was and launched in the hope that the target would still be there when the projectile arrived. An anti-tank guided missile could be fired from a position of cover, its flight path corrected by the operator watching its progress, its terminal trajectory adjusted to hit the specific part of the target vehicle most vulnerable to its warhead.
It could engage targets at ranges that no tank gun had ever matched in operational service. It could be mounted on vehicles far lighter than any tank, on aircraft, on wheeled carriers, on portable tripods carried by infantry. One soldier with a shoulder launch system could accomplish against a heavy tank what the FV4005 was designed to accomplish, at a fraction of the cost, from a position of relative safety, without requiring a 50-ton vehicle that broke itself with each shot. The calculation was explicit and was made by people who had the authority to act on it. The cost of developing and producing anti-tank guided missiles to achieve a given level of anti-armor capability was dramatically lower than the cost of the gun program. The tactical flexibility of guided missiles was dramatically greater. The technical problems of the gun program, the structural failures, the accuracy limitations, the ammunition handling, the recoil management, did not exist for missiles. The argument for continuing the program that had produced the FV4005 evaporated, and the argument evaporated at the same time that a broader defense economy review was identifying programs to terminate. The formal cancellation came in 1957 as part of a policy review that eliminated several other armor programs simultaneously. The logic was not disputed by the program's advocates because the logic was sound. There was nothing to argue with. The gun was extraordinary, and the vehicle was unable to support it, and missiles were better. These three facts, taken together, did not leave room for a counter-argument. The prototypes were broken down in the way that cancelled programs always disposed of their hardware. Turrets were separated from hulls. Components were sent to storage or to disposal. One turret found its way to a military educational establishment, where it served as a teaching aid, a physical example that instructors could use to explain to students the specific class of engineering problems that arose when a weapon's requirements exceeded the structural capacity of available vehicle platforms. For years, this was the entirety of the FV4005's legacy. A cancelled program, a broken turret in a classroom, a footnote in the history of British armoured vehicle development. The kind of thing that specialists knew about and nobody else had any reason to think about. What happened next to the surviving hardware follows a trajectory that would have been completely unpredictable to the people who designed the vehicle, and completely predictable to anyone who understood how cultural memory in the digital age actually works. The turret that had passed through a military college and then sat in a museum collection eventually found itself associated with a computer game. A game in which players operated historical military vehicles in combat against each other, and in which vehicles from all periods and all nations were represented with enough accuracy
that players developed genuine knowledge of their characteristics. The FV4005 appeared in this game, and its defining characteristic, a gun so large that it seemed physically incompatible with anything resembling a conventional tank, made it immediately distinctive in a medium where distinctive translated directly to popular. Players who had never heard of the vehicle, who had no particular interest in British post-war armoured development, encountered it in the context of virtual combat and found it memorable for exactly the reason that its designers had found it problematic. The gun was enormous, the vehicle was fragile, and the combination produced outcomes that were dramatic in a way that more balanced designs were not. The vehicle's profile in the gaming community was significantly larger than its profile in the historical record, which created an audience for the physical artifact that the historical record alone would never have generated. When the surviving turret at the museum was matched with an authentic chassis and restoration work began, the community that had formed around the game provided both attention and support for an effort that might otherwise have proceeded in the specialized obscurity that most military vehicle restoration occupies. In 2024, for the first time in approximately 70 years, an FV4005 moved under its own power. The engine ran, the tracks turned. The vehicle that had been designed in the early 1950s, that had shaken itself apart in firing trials, that had been cancelled before it could be completed, that had sat in a museum collection for most of the intervening decades, drove. The gun that broke the machine is still attached to the vehicle. It points forward, as it did when the first prototype rolled onto the test range in the summer of 1953. And the sight of it, the length of the barrel extending far beyond the front of the hull, the mass of the breech block visible through the opening of the turret, produces the same reaction in people seeing it for the first time now that it produced in the engineers who built it and the observers who watched it fire. It looks like something that should not exist. It looks like a problem that someone chose to solve through sheer scale rather than through elegance, and then discovered that scale creates its own problems at sufficient magnitudes. The problem it was built to solve, Soviet heavy armor that outclassed Western equivalents, was real. The solution it represented, a gun large enough to guarantee penetration of any armor then in existence or anticipated, was technically coherent given the constraints of the period.
The engineering difficulties it encountered were not failures of imagination or competence. They were the consequences of asking a ground vehicle to do something that ground vehicles at that stage of development could not do without destroying themselves in the process. The missiles that made it obsolete were a genuine advance in anti-armor capability, and the decision to pursue them rather than continue with the gun program was correct by any reasonable analysis. But the vehicle that the decision cancelled had demonstrated something that the theoretical analysis had not fully captured: that there was a limit to how large a gun a tank could carry and remain functional as a fighting platform, and that the FV4005 at 183 millimeters was well past that limit. The noise it made when it fired, audible at distances that normal gun ranges did not require safety cordons to protect, was the sound of a weapon operating at the boundary of what physics and materials would permit. The machine that shook and pitched and broke its own internal mechanisms with each shot was not a failure of engineering. It was an honest answer to a question that turned out not to have a satisfactory mechanical solution. How large can a gun be before the gun itself becomes the enemy of the vehicle that carries it? The FV4005 discovered that answer. The answer was smaller than 183 millimeters.